Hi, this is A. Somaya, working as Assistant Professor in the Department of Mechanical Engineering at Institute of Aeronautical Engineering, Dundigal. So today I am going to discuss about viscosity in fluid mechanics and emissions. So first of all, viscosity. Viscosity, how do you explain the viscosity? Generally, the viscosity is nothing but there is a fluid friction between the fluid layers. So the moment of the one fluid layer will be resisted by another fluid layer. That is known as viscosity. So viscosity, for ideal fluid, viscosity should be 0. So such type of fluid is known as ideal fluid because there should not be any friction between any fluid layers. So therefore such type of fluid is ideal fluid, but in we are coming across of all real fluids, therefore there must be viscosity. So that viscosity, how do you explain the viscosity and how many types of viscosities are there? What are the units of viscosity, etc. We will see today. So viscosity is that a property of fluid by virtue of which it offers resistance to the movement of a layer of fluid over an adjacent layer, as we discussed. It is primarily due to coercive forces and molecular momentum exchange between the fluid layers, and as flow occurs, these effects appear as shearing stresses between the moving layers of fluid. So basically, in a fluid, in a liquid, there are coercive forces, predominant coercive forces will be there, and molecular momentum exchange will be taking place. So due to these coercive forces, over a period of time during running, over a period of time, these coercive forces will become, will be developed and will appear as a shear stresses. So due to these shear stresses, the viscosity is occurring. So basically, because of coercive forces which are occurring in a fluid, so because of that, the viscosity is taking place. Another one is molecular momentum exchange will take place. So this coercive forces and molecular momentum exchange will differ from liquids to gases. In case of liquids, the coercive forces are predominant over the molecular momentum exchange. But if you consider gases, the molecular momentum exchange between the molecules will be predominating than the coercive forces. So this is how these forces will vary from liquid to gases. So now we'll try to find out the Newton's law of viscosity, otherwise expression for a viscosity. So here we are considering one is stationary plate. So this is a stationary plate. Okay, another one is moving plate. The top plate is a moving plate with the application of external force, capital F. Okay, whenever the y equals to 0, whenever the top plate is kept over on a stationary plate, then capital Y equals to 0. So when capital Y equals to 0, there will be no fluid movement. Otherwise, the fluid particles will stick to the both the plates, and there will be no flow occurring. So whenever there is a distance, whenever it is Y is moving at a particular distance, if you keep away, so then there will be fluid flow is occurring. While fluid flow is taking place at a particular distance, if you consider at a distance of y, and the differential distance dy, and the velocity you can find at a distance y, velocity is v. Small y, at small y, the velocity is v. And if you consider this differential distance dy, and it equals to differential velocity. So yet corresponding to dy there will be dv, corresponding to y there will be v. Similarly, at capital V, at capital Y distance, at maximum distance there will be maximum velocity, terminal velocity. So now whenever the fluid, whenever external force is applied, the fluid is moving. So experimentally the force application is given as, see, here there will be area, the area of plate which is in contact of fluid, there will be area, and area of this plate, and there will be velocity, okay, and at the distance of y. So now we will see, consider two plates sufficiently large that edge conditions may be neglected, placed at a small distance y, apart, the space between them being filled with fluid. The lower plate is assumed to be at rest, while the upper one is moved parallel to it with a velocity v. So by the application of force F corresponding to area A of the moving plate in contact with the fluid. So the particles of the fluid in contact with each plate will adhere to it, and if the distance y and velocity v are not too great, the velocity small v at a distance of small y from the lower plate will vary uniformly from 0 at the lower plate, which is at rest, to capital V at the moving plate. So experimentally, so this is given as F proportional to area into velocity by distance. F proportional. So the force, external force application is proportional to area into terminal velocity by distance between the plates. Okay. Now, so it may be seen from the similar triangles from the figure that the ratio of V by Y, capital V by Y, so can be replaced with the velocity gradient dV by dy. So from the similar triangles we can write this expression, which is the rate of angular deformation of the fluid. So this dV by dy can be called as velocity gradient. Also it can be called as rate of angular deformation and also shear strain. So this means dV by dy. If a constant of proportionality mu be introduced, the shear stress tau equal to F by A between any two thin sheets of fluid may be expressed as, so tau equals to F by A. See, actually F proportional to AV by Y, I am replacing V by Y, F proportional A into dV by dy, I am writing like this. So, but you can write F by A also, F by A, and this proportionality can be removed, that can be mu into dV by dy. So, where F by A is known as tau. F by A is known as tau. So, therefore, tau equals to mu into dV by dy. This is the expression, and this is also known as Newton's law of viscosity. See, equation 2 is called as Newton's law of Newton's equation of viscosity, and in the transposed form, it serves to define the proportionality constant. So equation 2 is tau equals to mu dV by dy. So in the transposed form, that means mu, it can be rewritten. See, tau equals to mu into dV by dy. So in another form, mu becomes tau by dV by dy. So that means where mu is known as coefficient of viscosity or dynamic viscosity or simply viscosity. So this also can be explained as the ratio of shear stress to the shear strain, otherwise ratio of shear stress to the rate of angular deformation. So that is to define the dynamic viscosity. This mu is known as dynamic viscosity. So basically tau equals to mu into dV by dy. This is known as Newton's law of viscosity. So in another form, mu can be written tau by dV by dy. So that is dynamic viscosity. So which is called coefficient of viscosity or the dynamic viscosity or simply viscosity of the fluid. Thus dynamic viscosity mu may be defined as the shear stress required to produce unit rate of angular deformation. See the unit of dynamic viscosity in SI units. In SI units, you can see mu is tau by dV by dy. So if you simplify this, you will find out Newton second per meter square in SI unit. Newton second per meter square. So this is a SI unit of dynamic viscosity, where tau units Newton per meter square. So dV by dy unit is second inverse. So therefore you will find out mu as Newton second per meter square. This is SI unit. We will see its further units. The SI unit is of mu is known as Newton second per meter square, but it's a metric gravitational system. Mu can be expressed as kilogram force second per meter square. So in the metric gravitational system, mu unit is kilogram force second per meter square. And similarly, in metric absolute system, the mu can be described as dyne second per meter square. Okay. Now, our gram mass per centimeter second which is also called as poise. So the unit of mu, unit of dynamic viscosity, also called expressed in terms of poises. So this is after Poiseuille. The centipoise is 1/100th of a poise. Centipoise is 1/100th of a poise. So in the English gravitational system, mu can be expressed as pound force second for feet square. So this is in English gravitational system. In English absolute system, the same mu can be expressed as pound/second for feet square or pound meter for feet second. So these are the four different units can be explained, can be remembered for in order to solve the problems related to the dynamic viscosity, related to the mu. So poises, okay, and metric gravitational, metric absolute, English gravitational, and English absolute system. Now, in numerical conversion from one system to another system is as follows: 1 Newton second for meter square is equals to 0.102 kilogram force second for meter square is equals to 10 poises. 1 Newton second for meter square is equals to 10 poises. So this we have to remember for solving the problems. 1 Newton second for meter square is equals to 10 poise. Okay. The ratio of the dynamic viscosity mu and the mass density rho, okay, so is known as kinematic viscosity. Kinematic viscosity is denoted by nu. Nu equals to mu by rho, where mu is dynamic viscosity and rho is mass density of a liquid. So mass density, the ratio of dynamic viscosity to the mass density of a liquid is known as kinematic viscosity. So here we can understand that in kinematic viscosity there is no force component. So here the unit of nu is meter square per second. So here there is no force component. But in case of dynamic viscosity, there is a force component. In kinematic viscosity, there is no force component. This is a difference between dynamic and kinematic. So where dynamic viscosity means it includes the force components, and kinematic viscosity doesn't consider the force. So that is a difference between kinematic viscosity and dynamic viscosity. On analyzing the dimensions of the kinematic viscosity, it will be observed that it involves only the magnitudes of length and time, not force. Only magnitudes of length and time. So here we can see various units of kinematic viscosity again, as we have seen for dynamic viscosity. So for kinematic viscosity, simply in SI unit, this is a meter square per second. So but in metric system, the nu can be expressed as centimeter square per second or meter square per second. So the unit centimeter square per second is termed as a stroke after GG strokes, and its 100th part is called as centistrokes. So therefore, kinematic viscosity can be expressed in terms of strokes. One stroke is equals to 1 cm square per second. Okay, therefore this is 10 power minus 4 meter square per seconds. So in the English system of units, it is expressed as feet square per second. So it's a numerical conversion from one system to another system. You can understand 1 meter square per second is equal to 10 power 4 cm square per second. 10 is that equals to 10 power 4 strokes, and 10.764 feet square per second. So here 1 meter square per second is equals to 10 power 4 strokes. See, the dynamic viscosity mu of either a liquid or a gas is practically independent of the pressure for the range that is ordinarily encountered in practice. However, it varies widely with the temperature. For gases, viscosity increases with the increase in temperature, while for liquids, it decreases with the increase in temperature. So, if you see the variation of viscosity for the liquids and for the gases, this will be quite opposite, because in liquids the predominant forces are quasi forces, and in gases predominant forces are molecular momentum exchanges between the molecules. So whenever the temperature is increased for the liquids, this quasi forces becomes weak, and therefore the viscosity of the liquid will decrease. In case of gases, if the temperature increases, these predominant forces are the molecular momentum exchange between the molecules. Therefore, where the viscosity will be rising. So that is the difference between liquids and gases. So with the function of a temperature. So but independent of pressure. But for liquids, For liquids, the pressure is independent. For gases, the pressure is a function of temperature only. So this is because of their fundamentally different intermolecular characteristics. In liquids, the viscosity is governed by the coercive forces between the molecules of the liquid, whereas in gases, the molecular activity plays a dominant role. The kinematic viscosity of liquids and of gases at a given pressure is essentially a function of temperature. So now we'll discuss about the Newtonian and non-Newtonian fluids. So after deriving the Newton's law of viscosity, tau equals to mu into dV by dy. This is Newton's law of viscosity. So then, based on this Newton's law of viscosity, we can describe the types of fluids. So if certain fluid is following this equation, tau equals to mu into dV by dy, then it is called as Newtonian fluid. This is called Newtonian. If it doesn't obey, then that is non-Newtonian fluids. So that is the difference. So how do you say? So common fluids such as air, water, glycerin, kerosene, etc. follow Newton's law of viscosity. There are certain fluids which, however, do not follow Newton's law of viscosity. Accordingly, fluids may be classified as Newtonian fluid and non-Newtonian fluids. So here we can see the graph between the tau, shear stress, and the rate of angular deformation or shear strain or velocity gradient. So here, see, for ideal fluid, the tau is 0. For ideal fluid, see, this is horizontal, perfectly horizontal x-axis. So this is ideal fluid, because where tau becomes 0, then such type of fluid is known as ideal fluid. Similarly, ideal solid means rate of angular deformation becomes 0. Then here dV by dy becomes 0. Therefore, this is a perfectly vertical y-axis. That is ideal solid line. This is ideal fluid line. So if the relationship between tau and dV by dy is proportional, then it is called as Newtonian fluid. It is a linear relationship. There is a linear relationship. And this is a non-linear relationship, therefore this is known as a non-Newtonian fluid. So if it is a tau versus dV by dy is linear, then it is a Newtonian. Here you can understand this is curvilinear, therefore this is a non-Newtonian fluid. This is not linear, therefore non-Newtonian fluid. Similarly, for plastic and thixotropic materials, initially certain yield stress, initial stress is required. After that we can find out whether it is following Newtonian fluid, Newton's law of viscosity or not. So if it is after applying a certain initial stress, we can decide. So see, initially we have applied this much of stress. After that, the plastic is following the linear relationship between dV by dy and tau. So, but whereas the thixotropic material, after applying the initial stress also, it doesn't obey. So therefore, this is it's an example. One example of the thixotropic material is printer's ink. So it's a non-linear, curvilinear path will take place. Here the relationship between for plastic is tau proportional to dV by dy after applying initial yield stress. Okay. So based on this, we can based on Newton's law of viscosity only, we are distinguishing various fluids. So such as Newtonian, non-Newtonian, ideal, solid, plastic, thixotropic, so many materials. For any fluid, if it is following tau equals to mu into dV by dy or tau directly proportional dV by dy, then certain fluid is known as Newtonian, otherwise non-Newtonian. Based on Newton's law of viscosity only, we are distinguish the fluids. So now in a Newtonian fluid, there is a linear relationship between the magnitude of shear stress and the resulting rate of deformation. The constant of proportionality mu, so in the equation 3, it doesn't change with the rate of deformation. In a non-Newtonian fluid, there is a non-linear relationship between the magnitude of the applied shear stress and the rate of angular deformation. So now we will go through a problem. A plate of 0.025 mm distance. So the distance is dy. So that is given as 0.025 mm. So into 10 power minus 3 meters. And from a fixed plate, so moves at a 60 centimeter per second. The velocity is given as change in velocity. There is dy. Change in distance is dy. 60 centimeter per second. 60 into 10 power minus 2 meter per second is the velocity, and requires a force of 2 newtons upon unit area, 2 newton per meter square. So then this becomes tau. Tau is 2 newton per meter square. So force for unit area is, that is shear stress, described by tau, 2 newton per meter square, to maintain the speed. So determine the fluid viscosity between the plates. So where we know tau equals to Newton's law of viscosity, tau equals to mu into dV by dy. So from this you have to determine mu. Mu is the unknown parameter, tau by dV by dy. So this we have to calculate. So here we can see that explanation. Distance dy is given as 0.025 into 10 power minus 3 meters, and velocity is 0.6 meter per second, and tau is 2 newton per meter square. So where we have applied the Newton's law of viscosity, where we have to calculate the mu. So all the numericals are submitted here. Mu can be determined as 8.33 into 10 power minus 5 Newton second per meter square. So this is a unit. If you want to express, since the dynamic viscosity can be expressed in pies, you have to multiply with 10 pies. 1 Newton per second, Newton second per meter square is equals to 10 pies. So if you multiply with the 10, it becomes 8.33 into 10 power minus 4 pies. So this is the answer. Now, so at a certain point in castor oil, the shear stress is 0.216 Newton per meter square, and the velocity gradient is 0.216 second inverse. If the mass density of a castor oil is 959.42 kg per meter cube, find kinematic viscosity. So here the given parameters are, the shear stress is given as tau 0.216 Newton per meter squares. Okay, and the velocity gradient that we know dV by dy is 0.216 second inverse. This is a unit. If the mass density is known as 959.42 kg per meter cube, find the kinematic viscosity nu. Nu equals to mu by rho. Okay, where rho is given. Mu only you have to calculate. How do you calculate mu? So for calculating mu, we know the Newton's law of viscosity. Mu equals to tau by dV by dy. This is approach. How do you solve this problem? See, tau equals to mu into dV by dy, where mu can be calculated as 1 because both are 0.216. Now kinematic viscosity becomes mu by rho. So where 1 by 959.42, you will get 1.042 10 power minus 3 meter square per second. So next, another problem. If a certain liquid has viscosity 4.9 into 10 power minus 4 kilogram force second per meter square, and kinematic viscosity as 3.49 into 10 power minus 2 Stokes. So what is its specific gravity? So here you have to calculate specific gravity. So here the given parameters are dynamic viscosity. See, specific gravity how much? So for calculating specific gravity, we need the densities. So we know the density of water, but we should know density of the fluid. So here certain fluid is given. Its density should be calculated in order to find out the specific gravity of liquid. So here the given parameters are mu equals to 4.9 into 10 power minus 4 kilogram force second per meter square. This can be converted into Newton second per meter square also. By multiplying with 9.81, it becomes Newton second per meter square. And kinematic viscosity nu is 3.49 into 10 power minus 2 Stokes. So 1 Stoke is 10 power 4. So meter square, 1 meter square per second is equals to 10 power 4 Stokes. So here, see, 3.49 into 10 power kinematic viscosity is 3.49 into 10 power minus 2 Stokes. So 1 Stoke is 10 power minus 4 into 10 power minus 4 meter square per second. So therefore the kinematic viscosity nu becomes 3.49 into 10 power minus 6 meter square per second. So 1 Stoke is 10 power minus 4 meter square per second. Therefore it will become like this. Now mu equals to multiply with 9.81 in order to get into Newton second per meter square, as this is in meter square per second. This is Newton second square per meter. Both are in SI units. So you have to convert them. Now nu equals to mu by rho, or mass density rho equals to mu by nu. So when mass density of liquid is known, then you can find out the specific gravity. So if you relate the for kinematic viscosity, so nu equals to mu by rho, where rho equals to mu by nu. So you will get 1377.3 kg per meter cube. Specific gravity of liquid becomes, see, mass density of liquid to the mass density of water. This is 1000, we know this is 1000, and this mass density we have calculated from this expression, that is 1377. Therefore 1.377 is the specific gravity of that particular fluid. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.